Hi everyone, welcome on Zoom this time. Welcome to CS330. Today we'll be talking about lifelong learning, which is a very interesting area of research, which is not very well defined, and we'll talk about it, and you'll kind of get to experience why that is. A few things regarding Zoom lecturing. If you have any questions, please raise your hand on Zoom. You can also write a question in chat. I won't be monitoring all of this at all times, but we have our lecture coordinator with us who will then speak up anytime there is a raised hand or a question posted, and we'll try to answer these. All right, so a few reminders. So this Wednesday will be our last lecture, and both the lecture as well as the instructor office hours will be over Zoom. So it will be in a similar setting like we have today. One thing that I would like to tell you is that we'll talk about frontiers and open problems in multitask and meta learning, and we'll have maybe 6 to 8 researchers who work on frontiers will tell us briefly about some of the recent papers, some of the recent projects, and you'll have a chance to meet them and ask them questions because it's all in Zoom, so it's a little bit easier to do it for them. So I would encourage you to participate and kind of get to know the people behind the research as well as the research that is happening. In addition, the 2 remaining reminders are that on Tuesday we'll have the project poster session, and then on Wednesday project review. All right, so the plan for today is the following. We'll talk about the lifelong learning problem statement. Then we'll talk about some basic approaches to lifelong learning, how we can address that problem. Then we'll talk about how we can do better than these basic approaches, also using some of the insights that we learned from the class already. And then we'll revisit the problem statement from the meta learning perspective. All right. So let's do a brief overview of the problem statements that we discussed so far. So we talked about multitask learning, where we try to learn to solve a set of tasks. And in that case, we had some kind of tasks that we had to learn that were given to us up front. And then we were evaluated based on the exact same tasks. So we are not really testing the generalizations to unseen tasks, but we train on a set of tasks and then we evaluate on the exact same set of tasks. And then we also talked about meta learning, where given an IID task distribution, we try to learn a new task efficiently. So we'll learn to learn different tasks. In that case, you were given a set of tasks at training time, and then at test time, you'll be tested, or it will be measured how quickly you can learn a new task that you haven't seen before. Right? So in that case, we are testing how quickly you can adapt to a new task you've never seen. However, in both of these cases, we assume that the tasks that you can practice on or that you can learn at the beginning are kind of given to you up front. You kind of have them at your disposal right off the bat, and you can sample them differently. You have access to all of them at all times. But in contrast, many real-world settings look a little bit different. In contrast, the way it looks is usually that you're given a task that you have to perform, and then after you perform that task for a little bit, you're given a new task, right? And you don't really have access to the old task. Now you have to focus on the new task that you just got. And then you do this over time, and every now and then you're given a new task that you haven't seen before, and you have to you're measured how well you're doing on that task, and you don't have all of the tasks up front available to you. So basically, our agents may not be given a large batch of data or tasks right off the bat. Instead, they're being revealed to you slowly over time. Right, a few examples when this happens. For instance, with student learning concepts in school, right? Like you go from one class to another, you go to Algebra 1, and then after Algebra 1, you pass your tests or your exams, then you go to Algebra 2. And then based on the content in Algebra 2, you're being evaluated how well you're doing in Algebra 2, and so on and so forth. You're not really given all the material all up front, and you're not being tested on all of the different classes. these are being revealed to you progressively. Another example would be a deployed image classification system that is learning from a stream of images from users. So in that case, it's an image classification system, and since maybe the things that users want change over time, and because of that, this image classification system will be seeing very different images over time. Right? We will also be getting new users. New users might maybe shift the data distribution a little bit. So we won't have access to all the kind of things that the users might want at the beginning. Another example could be a robot that is acquiring an increasingly large set of skills in many different environments. So in that case, you might have a robot that you deploy in a certain setting. For instance, you wanted to clean your kitchen, and then it learns how to clean the kitchen, and it gets better, and then you can use it for cleaning the kitchen. But then you want the robot to move to a different room and now do something else in that room, right? Maybe you wanted to do laundry now. So in that case, this new task is being revealed only once you move the robot into the laundry room, and then the robot is being evaluated on this new task that was given to it at the current time, as opposed to having all the tasks available up front. Another example would be a virtual assistant that is learning to help users or different users with different tasks at different points in time. So the virtual assistant, our preferences when we talk to it might change over time. We will also might need to adjust to different users, to constantly changing preferences, to maybe we want the virtual assistant to do different tasks and so on. So in that case, it's also being revealed new and new tasks every now and then. And then lastly, another example could be a doctor's assistant aiding in medical decision making, where not only the users might be changing their preferences and so on, but also new diseases might be coming in. For instance, a few years ago, a doctor's assistant didn't have to help with things like COVID-19. Now it should be able to handle that. So there might be new diseases, there might be new treatments and so on, and it should be able to adjust to these. All right, so these are some examples. Now let's talk about some terminology. So the terminology is actually not very well defined in this field. So we'll talk a little bit about this. So we usually refer to this as sequential learning setting, and you can see it under many different names. So some people call it online learning, some people call it lifelong learning, continual learning, incremental learning, streaming data, and I think there's probably a few more. The important part is that this is distinct from sequenced data. So for instance, text, where the words come in sequence. That doesn't necessarily mean that this is a sequential learning setting where you see the tasks that are being revealed to you over time. And it's also different from sequential decision making that we discussed in the case of reinforcement learning, where you might need to reason about the actions and how they're going to influence the future, but you can still have all the data available to you up front, and the data might not be changing over time, as it is, for instance, the case with offline reinforcement learning. So what is a lifelong learning problem statement? So actually, to kind of show you what it is and to maybe get you a little bit more engaged, we'll do a little exercise. So the exercise is the following. We'll split you into breakout rooms. We'll do it in a second. And in each breakout room, you'll pick an example setting. The example setting could be one of the example settings that I just discussed, these 5 examples that I gave, or you can think of your own example setting. And then you'll discuss a problem statement in your breakout room. And there are a few questions I want to ask you. So first, please think about how you would set up an experiment to develop and test your algorithm. Right? So kind of it's a question about how you would be, if you were to create a lifelong learning algorithm, how would you go about this? And how would you actually implement it in terms of an experiment? And then how would you test that it works? Secondly, think about what are the desirable or required properties of a lifelong learning algorithm, right? So what are the things that you would want to test, and what kind of things you would want to focus on when you develop a lifelong learning algorithm? And then third, it's kind of similar to what we already asked in A. How would you evaluate such a system? Right. So exactly what kind of numbers you would be plotting, so that you know that it's getting better, or it has the desirable required properties that you set. All right, so the example settings that I gave before are here. A few logistics, so we'll split you into breakout rooms. I think, I'm not sure how many people we have on the call, but I think we'll decide in a second how many people will be in each breakout room. And then let's say that if your the first letter of your first name is closer to the beginning of the alphabet, you'll be the person responsible for presenting the results. We'll give you all 5 minutes to discuss these questions. And then we'll ask you about your findings, and I'll take some notes. Is there anything else? If there's someone else who in your breakout room who would rather present it, that's also totally fine. Just if you can't really decide, let's pick the person whose first letter of the first name is closer to the beginning of the alphabet. All right, so let's split you in the breakout rooms, and I'll see you in 5 minutes. Everyone should be back now. All right, great, cool. I hope you had good conversations about the problem statement. So let me switch to the slides. Okay, cool. So I will ask groups one by one to tell me about desirable properties and considerations, and then also about the evaluation setup separately, and I will try to take some notes. So let's start with room number 1.
Yeah, I can talk about it.
Okay, cool.
Cool. So yeah, the example setting we chose was League of Legends, or any other game for that matter. And yeah, so the setting would be, we have a game bot that's learning how to play the game. Yeah, the reason why this would be considered lifelong learning is because there are constant patches that are released like once every month or so, and the bot has to adapt to adapt to play around that, like pick the right champions, pick the right game strategies, stuff like that. So for the experiment to develop and test the algorithm, it would just be like, the experiment would just be like game playing, and then we could like accumulate data over patches or like over games, and then yeah, it would have to like, we would see like the way we test it is whether or not it like learns to adapt after every patch is released, and it learns to play what the meta picks are, as in like what the best strategy is to play, and then yeah, pretty much we just had to see whether or not the bot changes its strategy as the game environment changes or the new patches or stuff like that.
Okay, I see. Okay, and so what would be, so you would be just measuring the pure performance after the patch, is that right?
Yep, that's correct. There's like a rating of how you play at the end of the game, so that rating would be the sort of the way we measure performance.
Okay, cool. I think that makes sense. So should adapt this game. It's difficult to write on this. So I should adapt this game after the patch. And then could you tell me, so would you give it like a certain window where it can adapt to the new patch, when it can kind of see what the new patch actually is, or would you measure the performance straight away?
Yeah, so if it needs to adapt quickly enough to like keep up with the rest of the players, like human players themselves take like about a week or maybe even a week and a half sometimes to adapt, and there's like a patch like approximately once every month or like once 1.5 months. So yeah, it would have to adapt maybe at least, if it adapts slower than the human players, then its ranking, the players, like the bot's ranking would go down in the system. But like if it could adapt faster or like even at the same time, its ranking would go up. So like the speed of adaptation is really a critical factor here, for sure.
Okay, but you would assume that within a week it should be able to adapt, and there is a new patch coming out every month. Is that right?
Correct, yeah.
Okay, cool. New patch. Okay, and will you ever evaluate it on the old performance? So let's say a new patch came out, will you also make sure that before that patch, with the previous version, does it still work?
Not really. It's like the game changes too drastically. I feel like the entire like play styles change and the way people like it's like a completely different game almost after every patch. I don't know. Like in a way, it's like there are common factors. It's like the main goal of the game is the same. You gotta go destroy the towers, like beat other champions, take the nexus. But like the way you play the game, like the strategies are completely different. It's like do you go into the jungle? Do you go take creeps? Or, it's like a whole different game, which is kind of what makes people addicted to it because it's like it keeps changing constantly over time. So it's like people keep like playing a new game every time. So people it makes people want to come back and play.
Cool, awesome. Yeah, this is a great example. Is there anything else that you discussed that you would like to add?
I think that's pretty much it.
All right, thank you. Let's move to the group number 2, to room number 2.
Can you hear me?
Yes.
Okay. Yeah. Group 2. We talked about how we would set up the experiment by just doing sort of an ablation test on having all the tasks at once versus doing the tasks in a random order. And similar to homework 4, how we had multiple episodes within a single trial, we would have multiple episodes, let's just say like 5 episodes, in a random order, and each episode has a different task that it has to solve. And then we would test the cumulative return on all of the episodes. So I guess in this example, 5 different tasks. And that's how we would evaluate our algorithm.
So it will be sum of returns across all the episodes.
Yeah.
Okay. And you would be you'll be comparing it to having all the tasks available to you up front.
Right.
Okay, cool. So what are the desirable properties?
We talked about how there might be a distribution shift in the tasks that you see earlier in training versus later on in training. So it should be adaptable to that distribution shift, and it should be able to either remember or forget certain skills that it learns based on kind of like an LSTM, I guess, if it like deems it unnecessary for future tasks it should forget. And then we also talked about the capacity of the model should be it should have a large capacity because at the end of training you would in theory be able to do all of the skills that you saw in the past.
Oh, interesting. So sorry, I didn't get that. So you're saying that the capability should be or the capacity of the model should be really big, or it should be big enough to be able to solve all of the tasks. Is that what you said?
Yes. Yeah.
Okay.
Yeah, that's all.
Okay, big enough capacity. Okay, and then in terms of a concrete task you would evaluate it on, you would take something like the task from homework 4.
Yeah, we were going with the robot example because we were talking about it in sort of a reinforcement learning context.
Okay, cool, awesome, thank you. Anything else that you would like to add?
No, that was all.
All right, thanks a lot. And let's move to group number 3.
Hello.
Hello. Hey.
We've taken over. So we were discussing the example B, sort of like a deployed image classification system. Specifically, we were talking about if we have a facial classification system, where we constantly get new images of both people we already have images of and new people, new faces, as well as an overall over time distribution shift of image of what images look like. So what we were thinking in terms of evaluating an algorithm for this is maybe keeping track of over time, keeping some sort of test set of images across a series of time. And essentially as we add more images, we sort of
filter or like split off some to add to the test set, while also perhaps like dropping off some of the older images with some like probability, with some probability, and essentially what we want is over time the algorithm should perform better and better on the newer images, or like on a like more.
Who will be controlling how it changes?
So like what we were thinking is like over time we want a bias towards perhaps newer faces in this classification system, as like maybe like faces that showed up earlier in the earlier in the stream of images may not be as relevant now, or like may not show up anymore in like actual application. In addition to like newer images perhaps being on average higher quality, or like different setups over time.
I see, that makes sense. And then the desirable property is that the algorithm does well on newer images.
Yeah. Yeah, and in particular, we sort of wanted to do better, I guess, on images that are essentially more common nowadays. So, for example, if like some individual person is like super relevant to facial classification nowadays, like I don't know, we want to be very accurate in terms of classifying who Professor Finn is, then we may want to essentially bias perhaps our test set towards those faces or towards those types of images.
I see. Okay, so like bias towards more important images, whatever that means.
Yeah.
Okay, I think that sounds good. And will you be still evaluating on all the images, or all people are also changing and their faces are changing? Will you always keep a certain set of images from the past to make sure that it does well on those?
Yeah, I think we like, I guess it depends a little bit on like the downstream application. But I'm thinking in most cases, we may want to like keep some old images, but also like slowly eventually like decrease their proportion. So like something I mentioned at the beginning was like maybe essentially have like a drop-off probability as we move on, like we have some chance of like gradually dropping each of the older images. So that way we have still like, or like we have more emphasis on the newer ones.
Yeah, okay. I think that makes sense. Cool. Is there anything else that you'd like to add?
No, not really. No.
Good. Thank you. And thanks for coming to the lecture, but also the Wednesday lecture will be also on Zoom. So, you know, yeah. All right, room number 4. I think that's our last room.
I guess I can talk about it. So we consider the sort of general classification setting where each task is a classification problem. So maybe a bit similar to the first situation where you have a student learning new concepts and the students sort of ask questions with discrete set of answers. In addition to what you mentioned previously, we thought that we'd consider 2 additional evaluation metrics. So one of them is sort of a forward transfer. So ideally, if we train in one task, that would improve performance for future tasks as well. And then on the other side, we'd also like to prevent catastrophically forgetting things about the old tasks. So if we learn on a task in the future, we'd like to retain knowledge, or maybe even improve knowledge for a task that we've seen previously.
Okay, yeah, that's a really good point. So prevent catastrophic forgetting, and to do this, you would keep I guess a set of images or a set of evaluations for all their tasks?
Yeah, exactly. We thought we'd have some a uniform least size set for each class that's just designated as a test set that we don't see during training, and then we can evaluate it sort of after training on each task.
I see. Okay. And how would you evaluate forward transfer? So you will be given a new set of images, I assume, or a new set of tasks, and then will you have some kind of burn-in period where you can adapt, or will you be evaluating this straight away?
We thought we'd just evaluate it straight away.
Okay. Okay. Cool. Is there anything else that you would like to add?
I think that's all we discussed earlier.
I'm not sure if I put the notes in the right column sometimes, but I tried to put them down whatever you're saying. Awesome. Thank you so much to all 4 groups. So one thing we can notice here is that first, the examples were quite diverse. I guess we have 2 image classification settings, but overall, we have robotics setting, we have League of Legends setting, image classification. So that's really great to see. And in terms of how to evaluate things, you can see that it actually changes quite a bit. Some algorithms look at backward compatibility, some don't. Like the group number 4 cared about preventing catastrophic forgetting. Group number 1 didn't really care about this because you only need to adjust to the newest patch. Then group number 3 had something in between. Then we see that different groups would evaluate the algorithm overall differently. Group number 2 would compare it to the performance that we see when we train on all of the tasks, versus with some other groups would look at how well our learning transfers to the next task and things like that. All right, cool. Yeah, so there is quite a lot of variability. So here are a few problem variations that I thought of as well. So one variation that we can have is whether we know about the task and data order, and whether it's predictable or whether it's just IID, or whether it's some kind of curriculum, or if it's adversarial to us and so on. So if it's IID, then it's just we're given new tasks every now and then, and that's it. They come from the same distribution. If it's predictable, then maybe it's something like the seasons, where you can predict that there are certain there's a periodicity to them. So like, summer comes every year and so on. They can come in the form of a curriculum where you get harder and harder tasks like you do in school, for instance, or they could be adversarial. Maybe that's the case in League of Legends, where maybe the new patches are so that the old strategies are not really working with the new patch. The other consideration is whether we have discrete task boundaries versus continuous shifts. So sometimes you can clearly tell that this task has ended, a new patch has been released, and from now on, the game is different. There's a very discrete task boundary. Versus if it's, for instance, a weather that is changing, it's maybe harder to say, at this point the weather has changed. The weather is kind of continuously shifting, and we could also have instances of both. Then we can have known task boundaries. So someone can tell us that they released a new patch, or unknown that we then need to detect in some way. And in terms of some considerations, a lot of them you talked about as well. So model performance. We can also look at data efficiency, how much data we need to achieve a certain performance. These are kind of similar metrics that we would use in standard supervised learning settings. We can also look at computational resources and the memory. So whether we need to keep all the old task data, all the old tasks in the memory or not, and what's the memory footprint of the algorithm. And then there are other things such as privacy, interpretability, fairness, test time compute, and memory. So these are things that are really important, and they're also important in supervised learning settings that also apply here. But one thing to note that I would like you to keep in mind is that there's actually substantial variety in the problem statement itself. And when we discussed some other types of learning before, like multitask learning, meta learning, reinforcement learning, multitask reinforcement learning, and so on, the problem statement is relatively rigid. Like it's well defined. We know what we are optimizing for, and if you look at different papers doing offline reinforcement learning, very often they would assume they would have exact same assumptions and they would be trying to solve the same problem. This is often not the case in the lifelong learning setting, and this is something to keep in mind when you read lifelong learning papers. All right, so let's go over the general definition of how a general supervised online learning problem looks like and how people usually think about it. And then we'll also talk about how what are the different ways to evaluate it that are kind of well established, and some of them you already mentioned. So for the general online supervised learning problem, for every task or for every data point, we'll observe our X, then we'll have to predict the Y, and then we'll get to observe the label. Right, so you get the X, and you have to predict the output, and then you get to observe the label only after that. This could happen in the IAD setting, where the axis, the probability of P of X, as well as P of Y given X, is not time dependent. This is this probability distribution doesn't change over time. Or it could be a time dependent distribution, where we have where our XT is coming from the distribution PT of X, and the same for YT is coming from the distribution PT of Y given X. So the distribution is changing over time, and we talked about different ways how it could be changing. It could be a curriculum, it could be adversarial, and so on. Then we sometimes also consider a streaming setting in which you can't really store your current pairs of XT and YT. So you kind of have to make a prediction, but you can't really store those. And there's various reasons for that. For instance, you don't have the memory to do that. For instance, you're trying to do some work on video, and video is streaming at very high frequency, and you don't really have enough memory to store all the different images that you see in the video. Sometimes you don't have enough computational resources to do that. There could be some privacy considerations where you can't really store images of people, for instance. Or when you want to study neural memory mechanisms that are biologically plausible mechanisms, how we memorize things and how we adapt. And in that case, we don't really have a very hard memory like we do in computers, where we can just store all the data. So when people study these kind of mechanisms, they usually also assume the streaming setting. So overall, this is true in some cases, but also not in many other cases. And most of the cases we'll be discussing today will be the cases where you don't really have to be in the streaming setting. You are allowed, or you can store the data as you see it. And we actually already discussed some of these things, for instance, in the case of replay buffers, where in reinforcement learning, you can be storing your experiences. You can keep storing everything you see in the replay buffer, and then you have algorithms that can retrieve that experience from the replay buffer and learn based on that. All right. Then one other note regarding the online learning problem. If we have observable task boundaries, if we know that a new task is coming, then we would not only observe the new data point XT, but we'll also know what task it comes from. So at some depicted by some task descriptor ZT, for instance, a one-hot vector or natural language description or something like that. All right. So then the next question is, how do we evaluate it? What do we actually want from a lifelong learning algorithm? And what people usually refer to here, there are two measures. And the first one is regret. So what people usually want is minimal regrets, or regret that grows slowly with number of tasks or with number of data points. And regret is actually a well-defined mathematical quantity. And it's defined as following: as a cumulative loss of your learner minus the cumulative loss of the best learner in hindsight. So this is very similar to what group 2 was proposing, where you can see how well your learner is doing at each task as the tasks come, and then compare it to the cumulative loss of the best learner in hindsight that would have had access to all of the tasks all at once. So mathematically, you can define it as, actually, I can just get the pen. Right. So here we have the cumulative loss of the learner. So in that case, at every time step or at every data point or at every task t, you'll be coming up with your parameters of your model, theta t. And then we'll be summing over, this will be the cumulative loss of the learner for each one of the tasks. So we're summing over all the tasks or all the data points that we see. And from that, we subtract the best cumulative loss of the cumulative loss of the best learner in hindsight. So in that case, you have access to all of the tasks up front. You can minimize your parameters across all of those tasks. And then the loss that you get for that is kind of the best loss you would have gotten in hindsight. So had you known about all of these tasks up front, what kind of loss you would have gotten? This cannot be evaluated in practice because we would always need to be doing that. But it's really useful for analysis. And in fact, the regret that grows linearly in T, in number of data points, is trivial. So one question I have to you is, why that is? Can you give me an example of an algorithm that produces a linear regret, or regret that grows linearly in T? You can just unmute yourself and speak up if you have an idea. Why does regret that grows linearly in T is trivial? Can you think of an algorithm that produces a linear regret? Any ideas here? All right, not so far. So let's maybe go through a little example that might clarify this a little bit. So the example will be the following. We'll be trying to predict, we'll be situated in a basketball game when you're betting on how many points will a NBA player score. And then your loss will be dependent on the difference between the absolute difference between how many points they actually scored versus how many points you predicted that they scored. All right. So for the very first game, you get to see this new basketball player that just joined the NBA. His name is Michael Jordan, but you've never seen him play in the NBA, so you have to kind of predict how many points he's going to score. You have to make a bet, right? So based on what you've seen so far, which is basically nothing, you're predicting that, given all the NBA players in the past, he might score something like 10 points, right? He's a new rookie. He seems kind of promising. Let's give him 10 points. That's your prediction. And then you actually get to see the game afterwards, right? And you get to observe how many points he actually scored. And it turns out that he scored 30 points. All right. So now let's say game number 2 comes about. And now you have to make a new prediction. And let's say that you're not a very, you're a very stubborn person, and you think that you're not really going to adjust based on the evidence that you've seen so far, and you'll just say, well, I'm going to stick to my guns. He's going to score 10 points again. Right? I'll just repeat the same bet. And then you get to observe the second game, and he actually scores 28 points. Right? And then the same repeats with game number 3. You've seen these previous 2 games, but again, you're quite stubborn. You want to stick to your prediction. You always say that he's going to score 10 points. He actually scores 32 points. All right, so in that case, we can calculate the regret. So let's see. Okay. So let's compute the first term. Okay. So the first term in the case of t equal 1, capital T equal 1 would be just equal 20, right? That's the absolute difference between what you predicted it was going to be versus what it actually was. And then t equal 1, we have 20 minus the best learner in hindsight. So the best learner in hindsight, you would have to predict the best kind of single number. That would be 30, and then the difference would be 0. So 20 minus 0, the regret would be 20. Right. So for t equal 2, right? So, or for capital T rather. So we'll be now summing over 2 games. In the original difference was 20. Now you get the additional difference of 18. So that's 38. Right? This is the cumulative loss of your learner, 38, minus the best learner that you could have in hindsight. You could have predicted an average of those two, so that would be 29. So then the difference would be 2, because 30 minus 29 is 1, and 28 minus 29 is 1 as well, the absolute difference. So in that case, regret would be 36. Right? And then for a capital T equal 3, we would have the difference be what it was so far. So that was 38 plus now an additional 22. So that's 60, right? And then the best learner that you could have in hindsight would have been the average. So the average across all of these would be 30, and in that case the loss would be 4. So in that case it would be 56. So now you can see that the regret here, it grew by 16, right? Here it grew by 20. And if we continue doing this exercise, here on average, you would be saying 10, versus here on average, you will be saying 30. So with every new game, you will be kind of getting a larger regret. The regret will be growing by 20. So it will be growing linearly in T. And so this is a very simple algorithm that is trivial, that you don't really adjust based on the evidence that you see. Your online learner is not really getting better with more data and with more tasks. It's just constantly outputting the same thing. And in that case, the regret is linear in T. Now, you could think of a different algorithm where instead you look at the best learner with all the games that you've seen already. So rather than for the second game predicting 10, you would predict the score that you had in the previous game. So you would say 30. And here for the third game, you would just take the average of the previous 2 games. And this is similar to follow the leader algorithm, where you kind of take the best algorithm or the best learner given all the previous data and apply it to the new data point. Right? Are there any questions at this time? All right, no questions? Okay, cool. So there is this other measure that is much more practical that people actually use quite often, which is positive and negative transfer. So, and these apply to forward as well as backward transfer. So the positive forward transfer would mean that previous tasks cause you to do better in future tasks. And this is something I think that group number 4 discussed, where you want to make sure that by leveraging data from the old tasks, you're getting better and better at new tasks. And this is compared to learning future tasks from scratch. And then we have positive backward transfer, which means that current tasks cause you to do better on previous tasks compared to learning past tasks from scratch. And then if you want to think about them as negative transfer, so you would just need to change the positive word to negative. And if you swap better with worse, you would get the definitions of negative transfer. So this is actually measurable, and this is often what people use in their papers. All right, cool. So this is the lifelong learning problem statement that is a little ambiguous sometimes. We discuss some measures of how people measure progress on that problem. Are there any questions at this point? All right, no questions. So let's talk about some basic approaches to lifelong learning. So there are a few very basic approaches that we can think of. For instance, we can store all the data you've seen so far and just train on it. And this is what we call follow the leader algorithm. This is similar to this codification of the sports betting game, where you're looking at the average of the points that Michael Jordan scored in the past games. Now, this will achieve very strong performance. This is actually a really good baseline. It's computationally quite intensive. You have to store all the data that you've seen so far. I guess in the case of the algorithm that we discussed before, you could be running some kind of running average. But overall, if you wanted to do this, apply it to more complex problems, you would need to store all of the data. And you would need to kind of keep retraining things all the time. Something like continuous fine-tuning can help here. So this is what I mentioned before. It could be memory intensive. It depends on the application. The other options that you have is just take a gradient step on the data point that you just observed. Okay? So you observe a new data point, you can take a gradient step with respect to that data point. Now, this is something that you actually know and you use it all the time. And this is called stochastic gradient descent. So in that case, it's really computationally cheap, right? You just apply a single gradient step. You can do this very, very easily. It requires zero memory, but it is subject to negative backward transfer, right? So as you're applying new gradients to new data points, you're not really keeping any old data points, and you're not updating your weights based on those old data points. So it's quite likely that you will forget about them. So in fact, people refer to it as forgetting, or as one of the other groups said, catastrophic forgetting. So these are the two terms that people often use for this case. The other con of this approach is that it can be very slow as well. All right, so let's discuss a very simple continual or lifelong learning algorithm that applies some of these concepts to reinforcement learning. And the paper is called Never Stop Learning. It's by Ryan Julian et al. And it takes a look at the data that was collected in QTOpt. So if you remember, we had these 7 robots that collected 580,000 graphs. And then we could evaluate how well it does on a particular scene. And here we picked a specific scene where you see those kind of objects. And with those objects, this algorithm with 580,000 graphs achieved 86% success. Okay. So now we try to see if there are any other settings where this algorithm doesn't work that well. So in this case, we looked at transparent bubbles, and it turns out that the transparent bubbles, it actually can't really solve them that well. So it only achieves 49% accuracy. Right? That hasn't been exposed to many transparent objects. It doesn't really know how to handle them. So now what we want to do is some kind of continual RL algorithm, some kind of adaptation procedure that would allow us to improve performance on those bubbles, right? On this new task that is presented to us. So the kind of high-level diagram of this will look like this. We have the old data that we had from the pre-training task, so this 580,000 grasps. Then we have our fine-tuning tasks. In this case, these are these transparent bubbles. And then we have to think of some kind of adaptation recipe that can also use our old policy that will achieve better results on this new data. All right, so this is the fine-tuning, or the very simple continual RL algorithm that we came up with. It's very, very simple. So this is how it works. So we start with the pre-training data set. That in this case, actually, we made it a little bit bigger. It's 608,000 graphs. And that's using that data set, we achieve 86% success in this original scene. Now we take that base data and we train the base Q function. So we just apply standard QTOpt and that's it. Now we'll do two things. We'll first copy the weights from this original Q function that we just learned with QTOpt. And we start, this will be our pre-training mechanism. And then in addition to this, we'll be taking the target data and we'll be collecting very little of it, only 800 grasps or sometimes even less than that. And we'll be mixing that data together with the old data in proportions 50-50. Okay, so we'll be getting this new mixture of data, this new batch that has a little bit of data from our target data, but also some base data so that we don't forget how to do it. And then we'll fine-tune our QTOpt based on that data. Okay, so it's very little data, but turns out we can do this. And then we'll have the adapted Q function that now was fine-tuned on this new data set, and it actually turns out to achieve very high success on the new task. Right. So here are a few evaluation scenarios that we consider. So again, we have the pre-train the pre-trained setting, where we achieved 86% success. And then we came up with a few different scenarios where this original policy didn't work very well. So we have harsh lighting, we have transparent bubbles, we have checkerboard backing that you can see in this bin here that makes it actually quite a bit tricky for the policy. We also modified the gripper, so it's a little bit extended here. And we also offset it by 10 centimeters. That actually looks really funny, like a Frankenstein robot, where the gripper is floating a little bit next to it. And here you see the performance that you get with all of these modifications with the standard QTF procedure. So now we'll apply our fine-tuning, and we see that we can increase, by just using less than 800 grasp, we can increase the performance with harsh lighting from 32 to 63%, and transparent bubbles to 66%, checkerboard backing to 90, extending gripper to 93, and offsetting the gripper to 98%. So you can see significant improvement with very small amount of data by just doing simple fine-tuning with Q function. Right, since this is a continual RL lecture, we can also apply it to a lifelong learning setting. So instead of just fine-tuning it once, we can fine-tune it many times. So what we can do here is we can start with our original grasping data set. We learn our Q function and we mix it with the new data that we see in the environment that we want to fine-tune to. And then we can take that Q function we just trained here that increase the performance, and then use that Q function to initialize and take the original data, mix it with the new scenario that we have in mind, and kind of keep doing this over and over. Now it turns out that we achieve fairly high result for this as well. So the performance keeps growing. So for the original harsh lighting, we have 32%, that increases to 63%. And then even though we copied this Q function as opposed to the original Q function that we had before, it turns out that this Q function is good enough to then be fine-tuned to these transparent bubbles and achieve high improvement as well. And this kind of procedure we can repeat. Right, one question you might have is, what about negative transfer? So have we ever tried in taking that Q function, for instance, and evaluating it in this scenario? And we haven't tried that. I would assume that it would actually go down significantly. We might be able to offset this by mixing some data from the previous experiences as well and figuring out kind of the right way to do this, to balance the data. But yeah, but we haven't evaluated this in this paper, and this is one of the examples of different lifelong learning papers care about different things and evaluate them differently. All right, so this is a very simple algorithm. So one question you might have is, well, can we do better than this? And this is
sorry, could I ask a question about the last slide?
Yeah.
I don't really understand. It's not my expectation that you would see the improvement as you step to the right. Like if that makes sense. So are you somehow leveraging, like in the offset gripper, are you somehow leveraging some improvements that you've made just by like diversifying your data set through checkerboard backing and extended gripper? And like if, for example, you just initialized, or is it like, did you just put them in that order? And if you initialized the offset gripper with the original purple model that you have here, yeah, if you mix the order around, do you see that same pattern?
That's a great question. So you're referring to the fact that these numbers here at the bottom keep getting higher, right? Yeah. As opposed to like these numbers, the improvement from here to here, it seems like these are improving as well. Yeah, I think this is not something that we intended. Probably if you mix the order of these numbers will also change. So there isn't really anything, I think, other than a slightly differently pre-trained Q function that you're getting at each step that would guarantee something like this kind of trend where the Q function gets better and better. If you look at the way we kind of the order in which we did these scenarios, this is actually very similar to the order that you've seen in the previous slide as to like how good of a performance they achieve at the end. So we just ended up kind of sorting them based on performance and then doing the continual experiment this way, but it will probably look very different if you do it the different way. Okay. Are there any other questions? Right, cool. So let's see. Okay, we don't have that much time. So can we do better than the basics? And the case study that we'll have is we'll look at negative transfer, negative backward transfer. This is something that we haven't really evaluated in the previous work, but this is something that the authors cared about in this work. And we'll see whether we can modify the vanilla stochastic gradient descent to avoid negative backward transfer. Right, so this is a paper from Lopez Paz and Ronzalo called Gradient Episodic Memory for Continual Learning. And the idea is the following. We'll store small amount of data per task in memory. And then when making updates for the new task, we'll ensure that I don't unlearn previous tasks. Okay, so this is kind of, I think that overall makes sense. The question is, how do you actually do this? How do you implement that? So how can we accomplish the number 2? So first we'll be learning this predictor that takes as input the current data point, as well as the task that's currently that this data point comes from. And then we're trying to find these parameters theta that will give us our prediction yt. Now, in addition to this, we'll also keep a memory for other tasks that we've seen in the past. So for any cave task, we'll also keep the memory that has a little bit of data from the task. So now for the different tasks, or for every data point, we'll minimize the loss as we usually do with the new data point. But then in addition to this, we'll have this constraint that says that the loss of our new function with our memory data should be less or equal to the loss that we had previously in the previous iteration on the previous data. And this is for the memory that was collected for all the tasks that we've seen before. Right? So we have this memory of tasks that we've seen so far, and we'll be evaluating the loss on that memory with our current parameter with our current neural net, and we're comparing this to the loss that we had in the previous iteration. And so we basically don't want to get any worse on the previous tests that we've seen. So yeah, in that case, basically loss on the previous task shouldn't get worse. In addition, what the authors do, they assume local linearity, and then they can actually compute this inner product between the gradients that on the current task as well as on the previous task, and if that inner product is greater than 0, then we should be good. And then they formulate it and solve it as a quadratic problem. All right. So then they do a series of experiments to evaluate this. So the problems that they consider are MNIST permutations, where you see a different permutation of MNIST, and you consider it as or MNIST digit, and you consider this as a different task. You can also rotate the MNIST and the MNIST digit and consider that as a different data point. And they also evaluated on CFAR 100, where you have 5 new classes per task. So every task is considered, new task is considered every time when you get 5 new classes. And then they look at backward transfer as well as the forward transfer, comparing to a few different baselines. And the total memory size that they have is 5,012 examples. Great. So here are some of the results. So their method is Their method is here called GEM. And first, you can see the overall accuracy, the classification accuracy is quite high compared to the baselines. And then if you look at the backward transfer, you don't really, for their method at least, you don't really see any negative transfer. Even if you see a little bit of a positive transfer, which is not the case for some of the baselines. And you see a little bit of the forward transfer as well. And then here on the right in this plot, you kind of see the effect of catastrophic forgetting, what's happening if you don't apply this additional constraint that they introduced. So here what you see in this plot is on y-axis is the accuracy of task number 1. So you can see that all of the methods achieve actually fairly high accuracy at the very beginning when you train on that task. And then on the x-axis here you see how many tasks you've seen so far. So you kind of see more and more tasks, and then you see whether the performance of this original task goes down as you see more data and more tasks. And you can see that for most of the baselines that is the case, the performance goes down, versus for their case, because they have this additional constraint that kind of makes sure that you don't really go, that the gradients you apply don't really forget the original task you had, the performance stays constant. A similar story, also we can see similar story for MNIST rotations, and we can also see similar story for CFR100, where you see that a lot of the baseline approaches actually experience some kind of negative backward transfer, and you can also see it here where the performance actually drops quite significantly compared to the method they introduced. So one thing to consider when looking at papers like this is kind of verify the assumptions and to see whether the setting that the authors were considering is actually well reflected in the experiments. So in this case, if we take a step back and take a look whether it makes sense to have a little bit of memory per task and so on. Does that make sense in terms of in the case of MNIST digits? Probably with MNIST digits, you could store all of the data set and all of the data that you see in its entirety, right? You don't necessarily need to have a little bit of memory that is somewhat constrained with size. It's very easy these days to keep all of this, to have access to the entire data set. So it's often quite tricky to kind of come up with the right experimental setting that then addresses or has the same assumptions that you had at the very beginning when developing this method. So that's something to keep in mind as well. You can also ask a question whether we can meta learn how to avoid negative backward transfer, and there are some papers on this. Here are the two that I would refer you to. We don't have much time to discuss them, but yeah, there are some interesting solutions there as well. Right, and in the last 8 minutes, we'll talk about how we can revisit the problem statement from the meta-learning perspective. All right, so if we look at this online learning formulation that we had before, there might be something that's a little bit wrong with it. And I was trying to hint at it during our breakout rooms. So with the online learning setting, we have to perform a sequence of tasks while minimizing the static regret. So what that means is that you measure the performance as soon as you're presented with a new task or with a new data point. So basically, you have to perform, you have to perform a task straight away, and then after you finish that task, you get to see the new task, and the performance is measured immediately. As soon as the task is presented to you, it will be measured how well you can do on that task. So it's measuring the zero-shot performance. But more realistically, what we might want to have is a setting where we get to learn a little bit. We have a little bit of time, a little bit of a burning period where you get to kind of see what the task is, you can adapt to it, and we want to measure how fast you can adapt and how well you can adapt in the task. So instead of just performing straight away, we'll try to learn new tasks as we see it. Okay. So in that case, we want to see that we start with very slow learning initially. It takes us a long time to learn this initial task, but then this evolves to very rapid learning over time. So over time, we want to be able to acquire new tasks much faster than we did at the very beginning. And this setting we'll be referring to as online meta-learning setting, where we efficiently want to learn a sequence of tasks from a non-stationary distribution. And this is discussed in this paper by Chelsea Finn, actually, and Arvind Rajasporn. All right. So it's important to note that the primary difference here is in evaluation rather than in the data stream itself. So you'll still get to observe the exact same data, the exact same tasks, and so on, but you'll be evaluated only after you have a little bit of time to adapt. So for this online mental learning setting, this is what we'll do. For every task, we'll observe a little bit of a training data set, this DTRT sub-T. And then we can use some kind of update procedure to update our parameters to produce the new parameters that take into account this little data set that we just observed, to produce the new parameters by T. And then we get to observe the data point, and then we predict based on these updated parameters, and then we get to observe the label. Now you can see that this last part of this problem is the exact same as the standard online learning setting. It's just the first part that is a little bit different, where we get to observe this small data set that allows you to find a better update procedure. And then the goal is similar to what we had before, except now we have this this function right here that we are also trying to we're trying to find the best update procedure for this. But we can still find learning algorithms of linear regression. All right, cool. So this is the loss of the algorithm, and this is the loss of the best algorithm. So the question is, can we apply meta learning in this lifelong learning setting? And if you recall the follow the leader algorithm, we would store all the data we've seen so far and train on it. So we can have a small modification. We can add the small modifications to this algorithm, and so that we can include meta learning in it as well. So what we'll do instead, we'll call it a follow the meta leader algorithm, FDML. And then we'll store all the data we've seen so far, but then we'll meta train on it rather than just training it. And then we'll run the update procedure on the current test. All right. So one question you might ask is, okay, we can do this, but what kind of meta algorithms should we use? Right? You learn about different kinds of meta learning algorithms, like black box algorithms, optimization-based algorithms, and so on. So assuming that our distributions of tasks is non-stationary and we might need to extrapolate, if you recall one of the previous lectures by Chelsea on different types of meta learning algorithms, it turns out that optimization-based algorithms such as MAML can generalize a little bit better outside of the training distribution as opposed to black box adaptation algorithms. So we'll use MAML and we'll try to see whether we can implement this follow the meta leader algorithm using. Right. So the experiments are as following. We'll have the colored, rotated, and scaled endless digits. We'll also have a 3D pose prediction problem where you get to see this image that you see here on the right, and you have to be able to tell what's the pose of the object in that image with respect to this red dot that you see. And then we'll also have the CFAR 100 classification where new task is considered every time you see a new class. Right, so the comparisons we'll have is you can train on everything, so train on all the data that you've seen so far. We'll also compare to follow the leader when we train on all the data that you've seen so far, and then we'll fine tune based on the current task. You can also do everything from scratch, so every time you see a new task, you train from scratch. And then we'll also compare to our algorithm, follow the meta leader. So first, we can look at the learning efficiency. So in that case, I think that shows how much data it takes to achieve a certain performance. So in this case, you can see that, so on the y-axis, it shows how much data there was, and to achieve a certain performance. I forget exactly what the performance was, but it was the same threshold for all of the baselines. And on the x-axis, you can see how many tasks you see. So initially, you start with tasks. We've seen 20 tasks, and you see task number 1, 22, 23, 24, 25, and so on. So now you can see that FDML algorithm, follow the meta leader, is able to get more efficient over time, eventually basically going to the regime where it can just learn a new task with a just few shots in a few shot learning regime, where it can just see a few examples of a new task and it can acquire this task very easily. And you can see the same for rainbow MNIST as well as for post prediction. In addition, you can also look at the learning proficiency, so the error that you see. And here on the y-axis, you have the error, but on the x-axis, you still have the task number. And you can see that also it's getting better and better as it sees more tasks. So it meta learns on it and gets better and better, and gets it can train on these tasks faster and achieve a higher proficiency. So follow the meta leader can learn each new task faster and with greater proficiency, and to the point where it starts to approach few shot learning regime. Right, so a few takeaways. We learn about many flavors of lifelong learning, and they're all under the same name. We run through the exercise showing, how you can come up with slightly different problem formulations, how you can evaluate these algorithms differently, and that's actually what you see in the literature as well. And even though this is a very diverse set of works, and sometimes they're not very comparable, they could still appear under the name of lifelong learning. And probably defining the problem statement itself is often the hardest part when working on these algorithms. You can also view meta-learning as a slice of the lifelong learning problem, and you can apply it to lifelong learning problems as well. And lastly, it's a very open area of research. So a lot of the things that we discussed today are very recent works, and there's a lot of people working on these kind of problems and reformulating them in different ways and trying to apply some of the techniques from other fields to see how we can apply this. But as of now, we don't really have many lifelong learning systems out there that are well understood and perform very well. Right. With that, these are the reminders that we have. Remember that on Wednesday we'll also meet over Zoom. We'll have some researchers talking about their recent work about frontiers in multitask and meta learning. So it should be very interesting. I encourage you to come and ask some questions.